The universe has made a mistake. Those are not my words. They belong to Dr. Wendy Friedman, one of the most decorated cosmologists alive. A woman who has spent 4 decades measuring the size, age, and expansion rate of the universe with more precision than anyone in history. She did not say them as a joke. She said them after reviewing the first data returned from the James Webb Space Telescope in the summer of 2022. And she has not fully walked them back since. That is where this story begins. Not with a galaxy, not with a nebula, with a number. A single number that our entire understanding of physical reality depends on, and which the most powerful telescope ever constructed has now measured twice and found to be wrong. The question is not whether James Webb made an error. The question is whether we did. For 30 years, we told ourselves a story about the universe. It was a good story. It had a beginning, a flash of infinite heat 13.8 billion years ago. It had a middle, matter cooling, stars igniting, galaxies spiraling into form across hundreds of millions of years. And it had a number that tied the whole thing together, a number called the Hubble constant, the rate at which the universe is expanding, measured in kilometers per second per megaparsec, named after Edwin Hubble, who first measured it in 1929 with a pocket watch and a primitive lens, and got it spectacularly wrong. We forgave Hubble. We refined the measurement. We launched the original Hubble Space Telescope specifically to nail it down. After decades of careful calibration, the scientific consensus settled on a figure, approximately 67 to 68 kilometers per second per megaparsec. Every model of the cosmos, every simulation of dark energy, every prediction about how the universe will end, all of it anchored to that number. We were confident. We published. We moved on. Except it isn't 67. The first hint that something was wrong came from a different direction entirely. Beginning around 2013, a rival group of researchers, using a completely separate method, measuring the brightness of a specific class of exploding stars called Type 1a supernovae, kept arriving at a different number. Not slightly different, alarmingly different. Their Hubble constant came back at approximately 73 kilometers per second per megaparsec, a gap of nearly 10% between two groups of extremely careful scientists using two entirely legitimate techniques. Cosmologists gave this problem a name: the Hubble Tension. It sounds clinical, academic. It is neither. If the tension is real, if both measurements are correct and the discrepancy is not a matter of systematic error, then our standard model of cosmology is broken. Something is missing from our understanding of the early universe, something we have no name for yet. But here's the part that nobody talks about. When James Webb launched on Christmas Day 2021, everyone in the cosmology community understood, quietly, what it would really be tested against. Not just galaxy formation, not just exoplanet atmospheres. The telescope would be used to resolve the Hubble tension once and for all. It had the resolution to see individual stars in galaxies 30 times farther away than Hubble could manage. It would measure the Cepheid variable stars, the pulsing stellar lighthouses that anchor the supernova distance ladder, with a precision that no prior instrument could approach. It would end the debate. In July 2023, it did, and the answer
was the last one anyone wanted.
The James Webb Space Telescope confirmed the higher number, not approximately, with a precision that removed virtually all remaining doubt about systematic error in the Cepheid measurements. Webb placed the local Hubble constant firmly above 70, consistent with the supernova-based measurement, inconsistent with the value derived from the early universe. The two numbers do not agree. Both are correct. The universe, as currently modeled by physics, cannot produce both of them simultaneously. Dr. Adam Rees of Johns Hopkins University, who won the Nobel Prize in Physics in 2011 for discovering that the universe's expansion is accelerating, stated plainly that with Webb's data, the Hubble tension now stands at a statistical significance of roughly 5 sigma. In particle physics, 5 sigma is the threshold for claiming a discovery. In cosmology, 5 sigma means the anomaly is almost certainly real. "We've now crossed a threshold," Rees said. "Something in our model is wrong." But that's not even the most disturbing finding, because there is a second layer to what Webb showed us, and it concerns something that happened to our earliest image of the universe: the cosmic microwave background, the faint afterglow of the Big Bang itself, mapped in extraordinary detail by the Planck satellite between 2009 and 2013. The Planck data gives us our best measurement of the early universe. From that data, using the standard cosmological model, called lambda CDM, physicists can predict what the Hubble constant should be today. That prediction is 67.4 kilometers per second per megaparsec, give or take a fraction. Precise, elegant, internally consistent. Except the universe, as measured by actual stars in the actual present, refuses to honor that prediction. What this means, what physicists are only beginning to say out loud, is that something happened between the early universe and the universe we inhabit now. Something that our model does not account for. An ingredient we have not identified. An event that left no signature we can read. The universe changed at some point in the last 13 billion years in a way that our best theory says should not have been possible. And this is where the data stops making sense. There are candidates. There are always candidates. Some physicists have proposed a period of what they call early dark energy, a brief pulse of anti-gravitational pressure in the first moments after the Big Bang that slightly altered the sound waves propagating through the infant universe, stretching the scale against which all later measurements are made. It is a viable theory. It is also entirely hypothetical. We have no direct evidence for early dark energy. We have only a gap that it might explain. Others have proposed that dark matter, the invisible substance that outweighs all visible matter in the universe by a factor of roughly 5, may not behave the way our models assume, that it may interact with itself, or with light, or with gravity, in ways that leave measurable residue in the expansion rate. If dark matter is not what we think it is, then the entire scaffolding of our cosmic model trembles. And some physicists, quietly, in the language of preprints and conference hedges, have begun to raise the possibility that general relativity itself, Einstein's theory of gravity that has survived every experimental test for over a century, may require modification on cosmological scales. That the geometry of space across billions of light years may not obey the equations we use to describe it. That Einstein was right about everything we can measure directly, and wrong, subtly, irreparably, about everything we cannot. Scientists have a name for that possibility. They call it a crack in the standard model. They do not fully understand what lies on the other side. Here is what James Webb actually is. It is not a camera. It is not a telescope in the sense that Galileo would recognize. It is a time machine with a 6.5-meter golden mirror cooled to 233 degrees below 0 Celsius, colder than the shadow side of Pluto, and positioned 1.5 million kilometers from Earth at a gravitational balance point called L2, from which it can observe the infrared light of galaxies whose photons left their source before our solar system existed. When Webb looks at a galaxy 13.4 billion light-years away, it is not seeing that galaxy as it is. It is seeing it as it was, 400 million years after the universe began, when the first stars were tearing themselves apart with the violence of ignition. We built this thing, a species that 66 million years ago hid from predators in the dark and did not yet have language. We built a mirror large enough to catch the oldest light in the universe, placed it beyond the reach of our own atmosphere, and asked it to tell us the truth. And the truth it told us is that we do not understand where we live. There is a version of this story that ends in crisis, a model broken, a discipline fractured, decades of cosmological certainty dissolving into revision. That version is not false. The Hubble tension is real. The implications are serious. The physicists who work on this are not sleeping easily. But there is another version. The version in which a 6.5-meter mirror, floating silently in the dark 1.5 million kilometers from Earth, cracked open a door that has been closed since the birth of science. The version in which the universe, for the first time in the history of our species, was forced to show us something it had successfully hidden. Not because we got lucky, because we were stubborn enough to build the instrument that made hiding impossible. Every great revolution in physics began with a number that didn't fit. The anomalous perihelion of Mercury didn't fit Newtonian gravity, and the crack in that model gave us general relativity. The ultraviolet catastrophe didn't fit classical thermodynamics, and the crack in that model gave us quantum mechanics. The Hubble tension doesn't fit lambda CDM. Whatever fills that crack will be something we do not yet have a name for. We are standing right now at the edge of what we know. The James Webb Space Telescope is still operational, still transmitting. Every day it adds to a dataset that is rewriting what we thought we knew about the age, shape, and fate of the universe. It has found fully formed galaxies in the early universe that should not have had time to form. It has measured atmospheric chemistry on worlds orbiting other stars. It has peered into stellar nurseries with a resolution that reveals individual stars being born in clouds of gas 1,000 light-years across. And it has confirmed, with 5 sigma certainty, that the universe as we modeled it does not exist. What does exist, what actually fills the darkness between galaxies, what actually drives the accelerating expansion, what actually happened in the first moments after the Big Bang, is still waiting to be named. We built a mirror large enough to see the edge of time, and what it showed us was that the universe had been lying to us all along, or we had been lying to ourselves.